we'll just begin.
Yeah, we are live now.
Okay, great. Thank you. Good morning, Ajit. Good to see you here.
Hi, Jonaki. Good morning.
Hi, good morning.
How are things?
Getting along. So we are welcoming, we are getting more and more participants coming in. There was a temporary glitch with the MTA web page, but we already have a lot of people waiting, I think, in the live stream, and we'll have more people in Zoom very soon. So we are very happy that Dr. Weng Kin could join us from Singapore. And this is, yesterday, Weng Kin, we shared with the audience that, we had 4 themes in this call we wanted to cover in this conference. And one of them was the connection between computational and mathematical thinking. And of course, when we thought of, we had to think of a speaker, who else, we could not think of anyone other than you for this topic. So we are really looking forward to that. And when we begin, I will introduce you formally. I can see people are still coming in, so maybe another minute or so we'll wait, if that's all right with you. Yeah.
Sure.
So just to discuss the format of the session, would you be comfortable? How much time would you want to continue talking? And then we'll open it up to.
Okay.
You have 1.5 hours.
I planned if I can take 15 minutes, 50.
Sure.
And I will leave about 10 minutes or so if there are questions and answers. And I would suppose that some might be actually typing their questions in the chat room. So maybe you just watch out for me what the questions are. And yeah.
Absolutely. Actually, we have slotted 1.5 hours for your session. So
is that right?
We want to speak for an hour, and then
I would like to do that, because I may be a little bit long-winded, because actually I've got so much to share.
Right. Wonderful. So you can speak for an hour.
Then I'll take that 1 hour.
Okay.
Yeah. Sure. Great.
Okay.
Thank you.
Great. So it is 10, but is it okay if we wait for another 2 minutes?
Sure.
If there are people still coming in, then I'll start. Okay, should I begin with the introduction then? Yeah, okay. Am I clearly audible to the audience? Okay, great. So it gives me great pleasure to welcome all the participants to the second day of this conference. We have very interesting sessions lined up for you to please attend and stay on. Now we are coming to the second keynote address of this conference and the first session today. And it is indeed an honor and a pleasure for me to introduce our keynote speaker for this morning, Dr. Weng Kin Ho. He's from the Mathematics and Mathematics Education Academic Group of the National Institute of Education, Nanyang Technological University of Singapore. Dr. Weng Kin received his PhD in computer science from the University of Birmingham in UK in 2006. His doctoral thesis proposed an operational domain theory for sequential functional programming languages. His interests include domain theory, general topology, programming language semantics, exact real arithmetic, category theory, algebra, real analysis, and applications of topology in computation theory. Notably, he has solved the open problem that questions the existence of a purely operationally based proof for the well-known minimal invariance theorem of nested recursive types in fixed point calculus and disproved the famous Ho-Zhao conjecture. He has a keen interest in mathematics education, particularly in the area of computational thinking, use of technology in mathematics education, video technology, and problem solving. He has recently published in several education journals on leveraging computational thinking in teaching and learning mathematics. He is the International Program Committee co-chair of the Asian Technology Conference in Mathematics, which is an international annual conference which brings together mathematicians and mathematics educators from across the world. And he actively lectures and participates in that conference every year. His interest and notable research work in the area of computational thinking and mathematics makes him the most appropriate speaker for addressing this particular strand of the conference. So I welcome you, Dr. Weng Kin, and thank you so much for taking time from your very busy schedule to address our audience this morning. So welcome to you, and over to you.
Thank you very much, Professor Jonaki. Thank you for your very kind words of introduction. And I would like to thank the organizers of the MTA for inviting me to deliver this speech. But the title of my talk today is about computation as a big idea in mathematics. So this talk, I would like to split it into two parts. First, I would like to speak about the theoretical underpinnings of computation proposed as a big idea in mathematics. And then we will look very briefly at some of the classroom implications. So a little introduction about where I work. It's a very nice place to work at the National Institute of Education, Singapore. Here we have a symbiosis of mathematicians and as well as mathematics educators working under the same roof. The advantage of doing that is that me being both a mathematician and a maths educator, we benefit from our research in our mathematics and also our research in mathematics education. So whatever teaching methods that we employ in the classroom is all research informed by the pedagogy. So I'd like to share some of these new findings that we have by proposing that computation should be positioned as a big idea in mathematics. And I hope that that would also be useful for our colleagues, especially teachers in schools in India. This is a brief overview of what I will be doing today. So in the introduction part, I would like to give a snapshot of things that happen in the math classroom in Singapore. And then I will lead you on to look at what big ideas in mathematics are and how it was at first proposed by Charles and what are these big ideas all about. And then I would list down the existing 21 big ideas in mathematics. And then I will go on to propose that, well, one should include computation because it is something that is so central to maths teaching and learning that we cannot ignore it. And it forms a very important strand that makes mathematics a coherent piece. Next, I will talk about some implications in the classroom, and then I'll draw some conclusions. Okay, now you must have heard many things about Singapore schools, right? It's very, very interesting because when you go to a Singapore school, all right, when they're having maths lessons, usually is really a lot of activities. You also have the usual so-called, drill and practice and teacher talk. But over the recent years, teachers in the classroom have seen that there are many other ways to teach mathematics. And a lot of mathematics activities are spun around things like problem solving, mathematical modeling, and group discussion, and so on, and maybe even guided discovery. So we'll now take a look at a few of the things or episodes in the maths classroom. I think it is also typical in India, perhaps. Okay, so that's what people in primary school would do. Maybe it's in primary 4, right? When I say primary 4, is a person aged 11 years old. Okay, and then you go on to the lower secondary school. With the lower secondary would mean is secondary 1 or 2, which means the student is aged about 13 to 14 years old. And then they progress on. That's when they are 15. They learn a little bit more sophisticated calculation, huh? And then this is what they probably would have done maybe in age 14 in secondary 2. They do a little bit of try and error, for factorizing a quadratic. That's a little bit lower. That's when they are about primary 6, huh? Which means they are 14 years old. They will find this kind of area. This is a little higher. This goes up to secondary 3 or 4, about 16 or 15, where they will prove some trigonometrical identities. And calculus, right? It's the techniques of differentiation that a 16-year-old will be able to do. And then you go on. In 17, perhaps you will use graphing calculators. This is situated in the Singapore syllabus, right, for what they call the Tier 2 H2 mathematics, which is actually a modification of the old Singapore Cambridge Mathematics C syllabus. So that's where they will learn graphing calculators and learn how to simulate random events. This is going down back lower to the secondary 3, where they learn binomial expansion. And then also down back to Riemann sums, right, which they learn in junior college in maybe age 17, 18, all right? So we have just actually, cruised through some episodes of mathematical activities that happen at different levels in Singapore schools. My question to you is, what is a common theme that's threading through all these episodes of activities you just saw? Now, as teachers, as mathematics educators in particular, what would you think that it is important for us to recognize existing themes that are common to these different episodes? Well, mathematics educators in the preceding century, we have recognized that maths teachers do require a very broad and deep knowledge base for teaching maths. So such knowledge will actually include knowing first the subject content, and this is the most important thing. I would think everybody here would agree. The second one is pedagogy, huh? And then you got to have a good knowledge of your students. What are the cognitive level, their cognitive development? You're also quite concerned about their learning, all right, in the classroom. So these are the 4 things that make a good teacher. So content knowledge of mathematics in itself, it includes the nature of mathematics, It includes a mental organization of the teacher's knowledge about the subject. So a teacher's integration of pedagogy and the understanding of this content that will form the basis as a foundation for the pedagogical content knowledge, which Sherman defines as this. It refers to the ways of representing and formulating the subject that make it comprehensible to others. So what is important is really an understanding of what makes the learning of specific topics easy, or maybe even for myself when I teach, sometimes it makes it difficult for people to understand. And also it refers to some of the concepts or the preconceptions that students at different ages, different backgrounds, they bring along with them. And this actually happens in the learning of even the most frequently taught topics and lessons. Now, this is very important because the teacher's perception of mathematics, it must be something which is coherent, is a connected whole, and it should be avoiding the situation whereby the teacher's knowledge is gappy, and that's extremely dangerous. For even if you have a very good pedagogy, you knew your students very well, and you are a master of orchestrating their learning in the classroom, and when you teach them the wrong thing, that's the worst thing that a teacher can do. Now, Charles, I think in 2005, I think that's as early as that, he proposed this idea of grounding teachers' maths content knowledge, and also the teaching practice that's centered around this set of what he calls big ideas in mathematics. So some say big ideas, some say big mathematical ideas, but just say big ideas in short, for short. What he refers in that particular seminar paper is that a big idea in mathematics is a statement of an idea that's central to the learning of mathematics, one that links numerous mathematical understandings into a coherent whole. So for my academic group back in 2019, we too support a association of mathematics educators. This association has been around for at least 30 years. And yearly we have something like what you have right now, which is a teachers conference. And Singapore maths teachers are all very eager to attend this annual conference because they come back to the institute where they've been trained. But now during COVID or post-pandemic times, now we are so used to having it online. So then we publish yearbook every year. And in 2019 in particular, we have this published around the theme of big ideas in mathematics. So then at that point, I have not yet thought so carefully about formulating computation as a big idea. But over the years, I thought this was something that's quite close to my heart and is actually getting more and more salient. And so just only this year, I started writing everything up, and it was recently accepted in the electronic journal of technology and mathematics. And this was, so what I'm presenting here is really fresh from the oven. Why is it important to be coherent? Now, the phrase coherent whole, it stresses a lot of building about a strong connection. Now, prior work by Hilbert and Carpenter already pointed out that the degree of understanding, even for students per se, is highly determined by the number and the strength of these topical connections. Now, it really makes a distinction between the expert knowledge and the novice knowledge. Because if we were to view big ideas as having connections with other ideas, and also understanding of which that nurture a deep understanding of maths, then teachers and students alike should no longer perceive mathematics concepts as a set of disconnected notions, disconnected skills, and facts. They should view it as a coherent whole because in that they can apply whatever they have learned in the topic to another seemingly distinguished or different topic. That's what we need them to learn. And that is the important thing about big ideas. In Charles' original paper, he actually totaled of 21 big ideas in mathematics that was intended for elementary and middle school mathematics teachers. And well, really understandably, we know that formulating this list is very non-trivial. Now, the interested reader may actually go back to the initial document to see how this evolved. But the long and short of it is that Charles asserts that, well, it is impossible to get one whole set of ideas and understanding that everyone, all mathematicians and all maths educators can agree on. But his main purpose of doing so is really like what we are doing right now in this conference. We really want to start and excite, a conversation among us so that it becomes a mainstream thing that we talk about when we talk about math standards, curriculum, syllabus, teaching and learning, as well as assessment. So this is something that we have to talk about. Now, here are the 21 items, the 21 big ideas that he actually teased out. And we are not unfamiliar with this. He's not saying that these aren't the only ones. That's fortunate. Otherwise, I wouldn't have inserted this computation as one of the big ideas. And certainly, we have seen from the snapshots in the Singapore classrooms that many of these things happen, all right? And they do have a bit of these big ideas coming in. But what I want to say is that for these snapshots which are shown, there is something else which also commonly threads through all of these things that they do. And it's not difficult to see, I'm sure by now, the common to all these episodes and activities centered around teaching and learning mathematics is that of computation. Now, before we actually get very enthusiastic to add computation in this list, let us now hit some warning that Charles actually put up. The first thing that he said is, look, the name of big idea doesn't constitute of the idea itself, but rather the big ideas themselves are really the statement that follow the name. Now, a big idea must importantly be central to the learning of mathematics. So which means that if we propose that computation is indeed going to be a big idea, it ought not just be a name to itself, but we need to specify its working definition. What does the big idea of computation mean? Probably what they mean more in the classroom. What are some of the implications of having computation as a big idea? How does it affect our formulation of, let's say, the lesson plan? How does it affect student learning in the classroom? How does it affect the sequencing of topics in the curriculum? Now we know, for example, that patterns, all right, this is very prominent. Now students see regularity, they see repetition, they see structure. So it's not difficult to see that, well, this is really important. The understanding is grounded on knowing all these observations are instances of patterns. So that's why big ideas for patterns make sense. It describes that relationship that generalizes all these math structures, and in such a way that it gives the person some ability to do predictions. So big ideas ought to be indeed big enough, so it creates the mathematical understanding that he actually wants to articulate. Big ideas must be useful to teachers. They must be useful to curriculum developers, test developers, policymakers, who in one way or another are responsible for shaping the national or state standards for mathematics education. So that's why I wanted to say and argue that to include this big idea in mathematics, include computation, it must not add on to the list in such a way to make it too many ideas. Nor should it be that it is too few, you see. And so now let me formally come up with a reasonable definition or a statement of computation as a big idea. So what is computation as a big idea? I would say that computation is a calculation, arithmetic or not, that's performed by an agent, a human or machine, following a well-defined model. That is to say that you are able to describe how an output of a mathematical function is being produced when it's given an input. And such a calculation must be of a certain finite nature. That is to say, it ought to be deterministic. It ought to, when given an input, produce a unique output by applying a finite set of rules in finite time. Okay, so that's what I qualify to be computation being the overarching idea. So already, if you look carefully at the list of 21 big ideas, there is one which is, I think, the big idea number 7, that talks about basic facts and algorithms. That really refer to some of the common algorithms or methods of computation. Let's say, for example, when a kid in primary 2 or 1, about age 8 or even 9, and they will start multiplying numbers together. Yeah, they multiply 3 digits number to a 2-digit number. So they have a certain way to do that. Then they learn long division. So these are some of the basic algorithms that they've learned. But if you just focus on that, that actually becomes a little too narrow. And that's why I'm asserting that if it is too narrow, you need a much more bigger or wider concept, for which this big idea number 7 might be subsumed under this even bigger idea. So let us just see how big an idea computation could be, all right, to really give a convincing case. Now, the first one that I actually see is what we saw in the episode. It was an algebraic expansion. Now, how would that be considered a computation? Well, certainly yes, because a correct expansion, for example, as the kid learns it, he or she must know what and how to apply the distribution law. So it's a distributive law. There is some association law as well. You need to know, how to group up things, and it doesn't change the value of the multiplication. And then you also need to know that there is this thing called the commutative law, right, for real numbers. So Mn is an Nm. You could do that, and then that immediately created more like terms. And you got the technique of grouping like terms together. So you're applying certain kind of, you would say, algebraic laws. But of course, in itself, we already have some rules for writing, or presenting these algebraic expressions. So there are a certain number of these laws that we apply, certain number of these rules that we need to use. And of course, the student need to stop doing it at some time, you see. And he or she must know when to stop it. So it's a calculation. So as I said, some writing convention is in place, some laws are there, and it does, of course, constitute of some kind of an arithmetic and algebraic computation. But less obvious, for example, and perhaps not very frequently talked about, is the notion of rewriting system. Now, computer scientists would be very familiar with this, logicians as well, because in logic, propositional calculus, you have a bunch of ways in which you can reduce logical formulas into simpler ones or standard forms. For example, one might talk about conjunctive normal forms and things like that. And so there are indeed some such rules. And again, one can apply these rules, all right? Maybe it's not going to be a unique path of application, but you can still apply it to reduce to some form. Or maybe, for example, on this slide, you can reduce it in this way. And another slide, the same expression, we reduce to the same final form, but through another different path, So these are very good. This is a very good way of seeing things, okay? Because rewriting system is very central to computer science. And of course, it is going to be applying a fixed set, a finite set of rules. It terminates, but it represents a kind of a so-called arithmetic manifestation of computation. Lots of other computations also take place, right, in the school. So, for example, in tertiary institution where we teach mathematics, now recursion, factorial function, where we ask the student to code a factorial function, that is done recursively. And of course, reanalysis students or even algebra students, defining sequences recursively, like the Fibonacci sequence, for instance, or even for numerical methods, for a numerical analyst, all right, producing, let's say, the Newton's method for solving an equation, all right, the iterates, all these things are done by recursion. So recursion is also very commonplace everywhere, all right, in mathematics. Even more so when you use computers to simulate random events using pseudo-random number generators. Now, of course, these kind of random number generators aren't really that random. They're in fact deterministic, but they are real-time automata, which is that actually they take in the input from the current clock reading and produce a number. There's nothing so non-deterministic nor probabilistic about it. And of course, we see, for example, MATLAB has such an implementation of producing a random number. But still, it is a computation. Well, computation of such simulation of such random events using a computer is rightly a computation because it is in fact deterministic, it's finite in nature. Now, to better understand computation as a big idea, then of course we also need some non-examples. So one of these non-examples is this. This is a flow chart. How could this not be a computation? But if you inspect this flow chart carefully, you're bound to get into trouble. Initialize the a to be 1, but as insofar as a is still greater than 0, please continue to do something to the a and update. But of course, if a is not the fixed point of this function, then you will see that this flow chart is going to do a lot of work. Indeed, in fact, it will work infinitely hard, but produce nothing. Okay, I would not say that this is not rightly a computation, but it's pretty fruitless computation. I would say for classroom purposes, it is at least a non-computation. Now, I need to say something about this because I'm going to repeat that somewhere down in the talk. Certain fruitless search for things, all right, okay, would be deemed to be not really a productive computation. So there's something to take note for my talk. Other things that I would consider as non-computation would be natural processes. Now, some of us will be a little bit angry with me for saying that natural random events are not really computation. For example, if you just throw a die with real physical die and then record the outcomes, that's not a computation. That's because I personally do not subscribe, and this is a personal opinion. I don't subscribe to the opinion of pan-computationalism, which postulates that, all of universe and its evolution, with all these physical processes are itself a computation. So I tend not to be so liberal about it. So I exclude that. I exclude that for good purposes because at least we need to have a well-defined definition to talk about. Otherwise, everything is a computation. That would be too wide. One of the things that I really need to pin down is, although we have a definition, we need to say what it is, when it happens, where it's going to happen, why do you need computation, and how do you execute one? So these are some of the things that really qualifies what the big idea for computation is in schools particularly. So I ask, in schools, are there a lot of opportunities for us to talk about computation? Well, the answer is yes, because we know that learning mathematics involves a lot of so-called rote learning of routinized calculations. Think about that. We do need students to be able to multiply, let's say, two numbers or add two numbers together at will, right? We wouldn't want them to think about how to do it, okay? And we also have working with fractions, taking the GCD or the LCM of numbers. They should know how to work this, quickly. So this sort of procedures, like, students should be able to remember, let's say, the cosine formula, by heart, hopefully. So these are some of the things. So there are a lot of specific algorithms suited for different purposes. But are all computations across all these topics of the same nature? I would say no. So that's what I want to say. What we mean by what computation is to realize what kind of nature of computational activities that takes place in the classroom. They are of a different nature. Consider the following simple tasks of solving the following quadratic equations. Standard thing almost. Which methods would you use? Well, a student at the lower secondary in Singapore would certainly not be able to solve this, because in their dictionary of algorithms, they would only know how to do it by trial and error, so-called using the cross method. Now, I didn't do that now, but I just put in algebraic form. Basically, they have to guess what integers a and b need to be fitted into this identity in order that you'll get an equality with x squared minus x minus 1 for all x. But of course, they can try all they can and find out, oops, you can't do that because there's some sign errors, all right? You try fitting in, all right? AB equals to -1. There's no way whereby a plus b is equals to 1. Certainly no way to do that, not at least when a, b are integers. Of course, then they will hunt all they can for real numbers because it's infinitely many real numbers. There's not even no bound to it. So the search space for this kind of try and error would have been infinite. And that would, of course, now hit back on my first point, that this is really not a computation. You're just trying your luck, And so you get stuck. But students, when they go up to secondary 3 in age 15, will suddenly realize that their life was made a lot easier. Well, why didn't you teach me that earlier? That was not the point. It was the realization that they have something more powerful should send them to think of where this particular algorithm came from. And this is exactly what I mean by having a computational mindset forces you to think, hey, this is so good, Where did it come from? This is a quadratic formula. You just feed these numbers in, you get the answer, or maybe you don't get an answer as well because of the square root. The contents may be less than 0. That will prompt the student to think further. What makes this clock tick? What are some of the advantages of this method over the previous one? So having a computational mindset is important for both the teachers and the students, because students will learn now to identify which of the activities are really computation and which are not. And among all those identified so-called computations that achieve the same result, they will now need to think carefully which is the one which is more efficient, and so that at the end of the day, they will make informed choices, in fact, intelligent choices of the computational methods. Now, for teachers, this is important because big ideas in computation help them shape their lesson development, and they will guide the students to effective computational choices. Knowing when do you execute a computation? For instance, this can be done in problem solving, all right? I gave this problem to my wife, My wife is a Mandarin teacher, Chinese teacher, who always claims that she's very bad at mathematics. But perhaps there's some blessing in disguise, I don't need to quarrel with her how to solve a maths problem. I gave it to her, one morning, and she took, she scribbled something on the newspaper and she got the answer, much faster maybe than even my undergraduate year 1 number theory students. Why? Because these number theory students don't dare to try. They were stumped. They were always fixated on thinking that the numbers ABC must be 3, right? 1/3 plus 1/3 plus 1/3, of course it gives 1. But the moment you say that there are some numbers distinct, they start to think, well, are there such numbers? But for somebody who doesn't know, she just tries. How does she try? She just tries with small numbers, you know what I mean? So computation starts by getting your hands dirty to try out some small cases. And indeed it does, because it works. Try out some small numbers. What happens? Well, basically, you'll argue that if you try out some small numbers, you get an idea of what the problem is. So the beginning computation sets you to understand the nature of the problem. And then you can quickly say, oh, wow, it can't be that all the numbers A, B, C being whole numbers are all greater than 3. Because the moment you have all greater than 3, what will happen? Then when you take the reciprocal, everyone will be less than a third. How are you going to reach 1, right? So give some sense of what's happening. So that means that at least one of these numbers ought to be, less than 3, right? Could be 1 or 2, can't be 1. You put 1, then, you get exceeding 1 on the left-hand side. So it ought to be 2. It forces it to be 2. So that's how my wife actually, got the answer. So just 2 first. And it reduces the search space immediately to a finite one. The same reasoning goes for the remaining sum. So that's how actually it went about. And for students who actually dare to use computation is the first step, to establish that kind of a brute force method. I would say that this is a heuristic that's actually very so-called not so frequently used, I would say, because they are afraid to do a search, an exhaustive search. But the computer doesn't care. If you have bounds to the search, then it's best handled by computers, shouldn't it? The next question is, why then do you need to use computation? An overemphasis of drill and practice often leads the student to believe that maths is repetitive. No, that's not quite true, because calculations, when performed without meaning, will leave the student a very bad aftertaste, and usually once they graduate from the school, they will forget about all the mathematics that they learned, for good. One of these things that I often hear people saying is that, after they graduated from school, well, where did we learn all this? Where did we learn how to apply all these trigonometrical identities? Why do we need to learn that in the first place, right? So students actually argue about it. It looks very mysterious and sometimes difficult for students to pick up. Why do we need to do that? So it's about why we need to learn something. Because unless they know that trigonometrical identities is of the rewriting exercise, and so that will be useful. That will be very useful, because that will engage them that they are doing a computation process, but they need to know why they are doing it. So as teachers, what we can do is that we should create more opportunities in another topic that will make use of this rewriting. For example, finding antiderivatives. That would be something that is really, useful for the students, because they need to rewrite the expression into a form that they can, fish out the antiderivative of known forms. For example, known forms refer to the basic trigonometrical forms in linear forms, and they should be able to rewrite the difference of the quadruples of cosine and sine into such functions. And unless they invoke their trigonometrical identities rewriting system, they would not be able to do that. They need to transform this as a difference of 2 squares, and then the squares will give you 1, and cos squared minus sine squared gives you cos of 2x, for instance. So this would then land up with a term that is desired. So there is a reason why they want to do that computation. This is just one of these things, that I saw students struggle, not knowing why they wanted to do that. And the other thing is, of course, also very crucial, and I said that before, is about the how of computation. It leads to 2 questions. One, how to compute something. The second one is, maybe amongst the different hows, you need to choose the best, right, to achieve a desired computation. So the concern is very real, and it has been actually investigated before. Why are we not teaching or creating teaching opportunities for students in the classroom to make a decision which computation road they should take? Even for university students, when we teach them things like sorting algorithms. There are many ways you can sort a list of numbers. Well, why would some ways be better than the others? Could you not invent a better way? Maybe this way is the best, but why is it the best? How do you qualify it to be the fastest? Now, for students in primary school or even secondary school, they will learn to appreciate this even at a young age. They don't need to learn all these sorting things, right? One example is this. This is learned first in secondary 3, 15-year-old kid. They learn this combination numbers, all right? So where would they use that? That probably was because they need to compute the coefficients in the binomial expansion of a plus b to the n, all right? For example, in this case, a plus b to the power of 8, the fourth term will require a choose 3 to be done. Of course, students will say, oh, that's easy, I just need to punch a calculator. But what they are then missing out is another learning opportunity. How can they do so mentally and very quickly for small numbers? Well, of course, if you just follow the definition, you just need to have to work out the 8 factorial, which I think is a very huge number, like in my opinion. I can't handle anything more than 30. And so then it becomes very difficult for the students. But students then quickly evaluate, if you're given a chance, how would you do that quickly? Well, that's easy to recognize that there's a whole pile of numbers that are common to the denominator and the numerator, which they can conveniently strike out. And using this, they quickly see that there is actually a shortcut. In fact, they will then quickly analyze, for given n and r, which of these two guys they should compute. They will start to appreciate that the Pascal identity is actually in work. They could have cancelled the other blocks of 3, right? Which one would they do? Then they'll realize that, this binomial coefficients is roughly symmetrical in the middle. And they got to think whether this R has passed the midpoint or not. And then they will be able to use the trick to compute this binomial coefficient very quickly. So as I said, there are many, many of these opportunities there, and they are all being motivated by situating computation as a big idea. And so therefore, I must go on to say something about this big idea, computation as a big idea. What are the implications in an actual classroom teaching? Just now, we just cruised through the many situations of the what's, the when, the how, where, But to make things meaningful for students in the classroom, that has got to a little bit more deliberate. We need to situate in such a way that the lesson is aimed towards meaningful learning. In that paper, which I have recently written up, I have identified at least 5 areas where you could do that in the classroom. But I think due to time constraint today, I would only have time to talk about one. But I'm very proud to talk about this one because this has been actually applied to schools. In fact, all of them has been. But this one in particular, the students find it was very useful. It's used as a method of consolidating a lesson or a couple of lessons. Let me explain a little bit. Now, one important component of lesson delivery is the stage where you help students consolidate. That is to say that the instructor will aid the student to summarize and to overview what they have learned during the past lessons, and using that as a kind of a lesson development. Now, one of the ways that the students can do so, usually, is that the teacher will draw on the board, a mind map or some, notes, summary notes in bullet point, this lesson you learned blah, blah, blah. Or they'll draw clouds, so the mind map with different concepts linking one another. That's good because that helps the student gather in one place all the relevant definitions and the concepts, or maybe the algorithms that is needed at one place. It's good for their revision, good to know where they have and what should they have achieved at that point. So each topic in mathematics in particular, has certain computational procedures. I already said that. Therefore, the big idea of computation lends itself very well because every topic will have some calculation. So how would that help the students connect all these seemingly, isolated nuggets of, procedures into one coherent picture? So I'm going to show you one example over here, which I think the students find it very useful. This also touches on one of the recent work I have with Professor Jonaki, who is with us. We investigated thoroughly how the spreadsheets, electronic spreadsheets like Excel or Google spreadsheet, let's say, it can be a very effective form of learning. It's a platform where students and teachers can use that and invoke computational thinking, invoke computation as a big idea in mathematics. Because why? Spreadsheets, you don't need to teach them very sophisticated programming. They're just this low enough, overheads for them, which they can learn on the spot, The important thing is that whatever that they learn in the spreadsheet, whatever formulas that they key in, help them understand functions, help them understand variable dependency, help them construct their mathematics knowledge in a useful way. So the emphasis is have a tool, have something that the students can have hands-on and construct a useful product. So this is where I need to share a bit of background information for this example. For Singapore, they have this subject called additional mathematics in and on top of the elementary mathematics that they learn. And these are 15-year-old students. And they will come across a topic where they look deeper into the topic of quadratic functions. And they will first time analyze where this quadratic formula about the nature of roots of the quadratic function, the quadratic equation, and graphing the quadratic functions and solving in quadratic inequalities and so on. Now, to help students consolidate their learning in this topic, what we can propose, all right, by invoking computation as a big idea in mathematics, is for students to build their own quadratic calculator. So how does it go? So in a typical lesson like that, the teacher would quickly show them what a quadratic calculator will look like in its final form. So this is a static slide. It is of no use. I don't like this. So what I have actually prepared is an actual spreadsheet, okay, which I hope you can see here. It's not very big, but you can see some of the things. So it's not static because quickly the teacher say, okay, Susan, what do you like your coefficients of x squared, x and constant to be? She says, well, I like the number 2, -1, and 4. And there you are. You actively, all right, obtain the graph. Well, I don't like it to be sketched over this interval -10 to 6. I would like it to be done over 5 to 9, for example. Can you always do that? Yes, you can. Can you do from -12, a wider range to 12? Is it obvious that you have some symmetry there, right? What are some of the properties? So you see, besides the graph, you also can see a table of values. You could also see the discriminant computed. You could see these words. These are not typed by the teacher. I didn't type it. They can change it, all right? If you don't like it, I can change it. I can change the quadratic coefficients. And different things come out. One real root only. The roots are displayed. The minimum point is calculated. The completed square form is there. Goodness, this is like a magical crystal ball, But this is not to be done by the teacher. The teacher shows it at the consolidation stage and set the student to work. Look, you need to produce this for me because you're going to use this for your own revision later for your exams. Don't you think that this is a good calculator they were very proud of if they are able to manufacture it? And so the subsequent lessons will be to develop to teach enough skills for them to program this. It's not that difficult. They will quickly learn that in order to create the table of values, they will have to use progression number patterns that they learn from another topic. They will learn some of the simple graphing features of choosing, for example, a quadratic spline to interpolate all these points. It's a bit of cheat, but it works. And there are some hidden formulas under each of these cells. You know, these are not magical. Things don't fall from the sky. They are all there. And the students need to know how to program them. And so this is good because the programming overheads are very low, but the production at the end of the day is big. They can see and they most importantly can use it. So this is what I mean by a very meaningful kind of a lesson consolidation for the students, because they can construct something. If a teacher saw that this has been done nicely by the students or group of students, he or she can be very sure that the students must have understood the entire topic of quadratic functions for free. So it's used as an assessment tool as well. So finally, I've come to the ending part. And of course, in this talk, what I have done is that I've proposed that computation should be included, and seriously should be included, in the collection of big ideas in mathematics. What we have done is that we have situated computation as a deterministic input-output process of a finite nature, determined by a finite set of operational rules, terminating in finite time, and then we are able to articulate the essence of this new big idea. What this definition is good is that it helps us clarify through different examples, and perhaps even some non-examples, and then we qualitatively describe what it means in the classroom. What is computation? When do you use it? Where do you use it? Why do you want to use it? How do you choose a suitable and efficient way of computing? All these starts to help us establish a kind of centrality of this big idea of computation right in our schools. And so if we believe that computation as a big idea in mathematics is indeed very significant, it ought to have an impact on the way that we teach and on the way that students now learn mathematics. We should not say, oh no, my teacher used to teach me this topic in this way. But now we live in the current century where technology, with computers, where we are talking about smart nation. So therefore, we need to relook at the ways that we teach and relook at the sequencing of the syllabus, factoring computation as a big idea in mind. Computation is everywhere in mathematics. And so, of course, it becomes a convenient link among the different topics in mathematics. And I have hopefully convinced you that this is something that is useful for us as teachers and also learners of mathematics ourselves. Here are some of the works that I have cited in this talk. You may have a look at it. Some of these are pretty recent as well, especially those which I have, even this one, the last reading, we have not yet even presented this at the conference, which is going to happen in Prague at the end of this year. So having said that, all right, that's actually the come to the end of the talk. In fact, I have only shared half the amount of materials I have for that new paper that I've written. There's still another half sitting there, but I thought this is a good overview, and I think teachers, I hope at least that teachers would find it useful. So thank you very much for your attention, and I will hand the session now over back to Professor Jonaki.
Yes, Weng Kin, thank you so much for that wonderful presentation and for really telling us what are these big ideas in mathematics, and for creating with theoretical underpinnings and logically why we should include computation as maybe the 22nd in the list. Before I sort of conclude your session, there are many interesting comments and questions. So I'm going to read them out from the chat box. So Pankaj Ranjan says that the phobia, it's a comment, phobia are also created by parents and members of society in the brain of child very early. Please tell how to overcome the problems, especially in economically and geographically areas which don't have access. So Pankaj, would you like to unmute and ask your question yourself so that you can make it clear?
While teaching, as a teacher, I have learned that economically backward area or geographically tough area, parents and grandparents say that mathematics is a very tough subject and it is very boring. So we are very unable to motivate the students how to get these problems sort out. So I have raised this problem.
Yeah, I understand where you are coming from, and it is a very good question. Because in India there's a large, range of backgrounds, from different economic areas and different geographic considerations. All right, and I certainly appreciate these differences. It's actually quite the same in Singapore as well, right? Where there are equity issues in the education, and there are students coming from different backgrounds. And generally, when we are coming to the topic of motivating the students and also cognizant of their cognitive developments for young children, intrinsic motivation for students to learn mathematics therefore become very important, especially during the early childhood. So in mathematics education per se, what we can say is that we can make use of computation as a big idea by looking at the effective domains of learning mathematics. That is to say, it is such that they'll create enthusiasm, is to create that yearning or that curiosity at a young age without creating fear for the subject. So that, for example, can be done when we speak about computation. We often think that, computation must be to do with programming. And if, for example, if the kid doesn't have a computer, then that's it, you can't even start talking about that. In fact, there are a lot of lessons that I've crafted which does not need a single computer program, not even one. You can do it using what we call unplugged activities, okay? One classic example I've done for very young kids, like, for example, 13 years old, when they want to learn about the topic of irrational numbers, I challenged them to use only the numbers 0 and 1 in decimal form and create for me an irrational number. So, of course, I have a different definition of what rational number is one in which the decimal representation is either truncated or it has got eventually periodic, So students actually want to find out rules for which to defy the definition of rationality. So they just construct the numbers. They were very excited. So I remember the class where I actually, with a teacher, we co-teach that class. They were just very mixed ability students, not that they are very good with mathematics, but they get very enthused. They say, wow, this is very fun. This is like a game, And so they split it into groups and they start playing, start constructing their own irrational numbers. And then the nice thing is, at the end of the day, when they show their classmates what their numbers are, a lot of the numbers coincided, right? It's very interesting what they type, very interesting. And they start naming these numbers after themselves. So they had their ownership that they're learning something which is not directed by the teachers top down. It's not because the teachers are forcing me to learn, but because I wanted to do it myself. A few of the other episodes that I had with students with regards to their motivation is that there was one session where we used Excel spreadsheet to learn number patterns. So this group of students exited from the classroom. They were so excited. They told us, the researchers, they say, we never had a lesson like this before. This is maths, you mean? This is so fun, because I'm not bothered with doing maths right or wrong. I just bother about, making the machine work for me. I said, yeah, that's maths, and they were also excited. Can we have more? That's what they said. So I hope that my answer to your question is that there are ways, but it is very important for us to make use of computation as an opportunity for students to learn it the fun way. Yeah, thank you.
Thank you. Thank you for answering and responding to that so well. I would like to go, there are a lot of questions coming up, so I'm going to the next question from Garima. When we talk about big ideas in mathematics at the higher level, for the undergraduate, for instance, do the big ideas remain the same, or the advanced understanding requires something more? According to the, is justification, for example, a big idea in mathematics? So in terms of at that level, undergraduate level, how do you see the big ideas in mathematics?
Okay, very good question. Excellent question, this is. Because already Charles preempted that in his original formulation of big ideas, because his big ideas were intended for middle school and for elementary school students. But certainly big ideas, transcend at all levels. And at different levels, the manifestation of that big idea will take different forms. As I said, there's no hard and fast rule about, formulating the name of the big idea, because I don't think the name is that important. I think it's whatever that is the description of that idea, and that most importantly, whichever idea that we are talking about, that idea ought to be central to learning mathematics, in the sense that it has to be ubiquitous in every area or most areas where mathematics pop up. Example, so a very good one that is that Charles formulated is that of proportionality. Now you can think of proportionality in many different ways. In a simple, let's say for example, when we mix orange juice, right, with syrup and water, there's a fixed ratio, right? There's proportion. I get more orange juice. What must I do? I have to proportionally increase the constituents, right? That's what they do. But isn't that also the same idea when we do sampling, of random sampling, right? When we have, a knowledge about the proportion of voters in the population, what happens when I take a subset of it? Should it not be reflective of what is happening in the population? So proportionality prevails, but in a different form. So if supposedly we are talking about computation as a big idea in schools, when it come up to the level of the university mathematics, then it manifests in a different way. Perhaps they might be challenging them to do more sophisticated kind of, computation, or a deeper rendering of, numbers in investigating things. One of the things that I didn't have time to talk about, as you will see in the list, is that big ideas for computation as a big idea help students use computation to formulate conjectures, to test out whether a conjecture is there. Is it going to hold? How does it support in discovering solutions to a problem? So these are things that I think would be useful. We can have the same name, but at different levels where we are teaching students, they can actually manifest in different ways. I hope that answers the question.
Okay, yes. Right, thank you. So we will go to now there's a comment from Venkatesh Kamath who says that students learn to solve problems using algorithmic thinking without really understanding it deeply. It helps them to crack the exams. And connected to that, there is a question from Jam, which says, where he's asking, when you talk of big ideas, would you use computation and algorithm equivalently, or would you distinguish between them?
Okay, I do not make a very big distinction between algorithm and computation, because I have said that, well, essentially algorithms are recipes with, finite set of instructions, you can carry them out insightlessly, all right, and then get the answer. And certainly what was being raised is that if you already knew an algorithm for doing things, you can do it fast. And that's the whole part about an algorithm, right? It helps you crack, problems quickly, even in competitive exams, all right, or high-stake exams, even in Singapore. That's what they do. And that's why people are sending kids to, private tuitions, just because they can be drilled to perform these algorithms quickly, right? They identify the question types and they will then execute a certain solution template. Now, that's what actually I have written in another paper, is that, yes, that is a good beginning. It's not lousy. Nothing is wrong about that. Nothing is wrong with learning things using algorithmic reasoning. Nothing. In fact, we all start from there. But we should not stop there. We should continue to push the kids from using algorithmic reasoning, that is to just apply the formula, to move on to the end of the other spectrum, which is problem solving. Because in problem solving, you do not have an algorithm. You don't have a ready solution. So what are you going to do? Then you should actually start with something that you really have, right? And then to move on in creative ways, either to modify the algorithm or to question where that algorithm came from. What are the underlying assumptions for that method and why it did not help in this case? Then the student can be pushed to move to the other end of the spectrum to be creative problem solver. And in that paper, I state very clearly is that you can use computational thinking as a passage that helps the students move from the algorithmic reasoning to creatively founded mathematical reasoning. So they can be able to create new things themselves. One of the things that I would really love to introduce to teachers is the program called Frogorithm. I have actually used it just now. It is actually a very low cost kind of programming. I wouldn't even say it's a language. It's a dynamic flowchart. And the students can use that to program and to learn new things. One of the things that I have created was to ask students to do up a quadratic formula calculator, just a quadratic formula flowchart. Could you do that? And then use that flowchart to investigate the following problem. Which quadratic equations with integer coefficients will always produce rational roots? So that was something that they didn't know. Yeah, why is it that sometimes it's very lucky for me to try the cross method and it works? Is it because I'm lucky? Is that a necessary and sufficient condition for that to happen? So that was a problem. And so then the students went through the flowchart, went into looking into the bolts and nuts of the program and make the deduction, which part of the program was key to determine the nature of the roots. They did that, and so it helped them. But certainly, we don't stop students from learning algorithmically, but we do not let them stop there. That's my point.
Okay, great. So there is a continuation from JAM, which asks, should we also single out and highlight reasoning about procedure / computation as an element of math pedagogy?
No, I think the detailed answer, he covered that
Right.
point as well.
Okay.
I was emphasizing, he was talking about reasoning about algorithms and procedures pretty much, which is exactly what I was having in mind.
Yeah.
Thank you very much. That is a comprehensive and beautiful
You're most
answer.
welcome.
Thank you. And Ravi is asking, is the idea of finite convergence necessary in the definition of computation? For example, a recursive algorithm to approximate the square root of 2, which goes back to like 3,000 years, would be a nice exercise at the school level. Ravi, you could ask also if you want to further elaborate on the question.
It's fine, Jonaki.
Okay.
Yeah, I think the answer is very well formed. Certainly, because that finite convergence would constitute of the fact that the algorithm have to stop somewhere. Now, however, I need to qualify myself. Okay, being a practitioner in exact real arithmetic, when we need to compute a real number isn't that real after all. A real number in its content is infinite. Okay, nobody can compute a real number. well, at least not in showing the actual totality of the real number. Every real number that we are trying to attempt to compute is of a finite nature. So think of computing pi, for instance, all right? Every time you need to print out some stuff, all right, you need to wait for some finite time, and some digits have to appear somewhere, and the algorithm cannot read infinitely before producing one digit. If it does so, then it is a useless algorithm. All algorithms are of a finite nature. That is to say, and this is a very interesting and very deep result, is to say that every algorithm is continuous. In fact, it is Scott continuous. Yeah, it's continuous with respect to the Scott topology. Yeah, thank you.
Sorry, may I quickly interject? Doesn't your PhD address precisely these questions? So
yes, it does. It does. So, it does. Yeah.
Yeah.
Okay. Okay. There's another question from Purna. As a mathematics educator, the biggest challenge I'm facing as of now is how to create an intrinsic motivation for the present generation students to learn math. Relating the math lesson to the real world or life, use of ICT, etc., have been applied. But yet, if you have any new insights on this issue to motivate the present generation students, kindly educate us. And she's thanking you for
surely I have, because that is also one of my concerns. Yeah, it's one of them, but I want to say a little bit more. I wanted to say that one of the things that I have been thinking about is to use computation as a big idea into solving problems in the real world context. Okay, I always give a very simple scenario for students in lower secondary or even primary school. I say, look, this is very interesting, you know. When you go to the Starbucks and you start ordering your coffee or your tea, you know, in different various combinations, you may want to have whipped cream, you want a latte, or you want a cappuccino, or you want black tea with no sugar, blah, blah, blah. How is it that the person could immediately ask you how much you need to pay, right? That's very interesting. It's not because the person is very, very quick with his calculation. There was something there at the cashier which could immediately deal with that problem. Could you please help me create a calculator that does exactly the same thing? So that's very interesting. The students say, okay, well, then in the first place, what do I need to do? I need to go to Starbucks to look at what are the items sold there. I say, please go ahead and make a list. Try to find out the prices. Input those prices in your Excel spreadsheet. Create this thing, which could help, you know, key in the quantities. Are you taking away? Are you eating here? You know, all these things factor into it. After the students gone through the exercise, they fully appreciate that actually, the maths, the very simple algorithm of multiplication and addition is so useful. They now then see, you know, how to give discounts to people. You know, if you have a promotion code, how do I actually entertain that as a discount given to the customers? They learn that then, oh, this is something useful, and they wanted to do it. So it's nothing of a rocket science happening in the school. All they need to know is that whatever that they have picked up, or these little bits and pieces, are now coherently connected into one useful body and to produce a useful product. They can do that. They can start now bragging, you know, that next time they can be computer programmers for all they know. But certainly a very important motivation, rather than to stay dry about just the process of doing all these mathematics, but to see that they are being used in real world context. Yes, I advocate that.
Yes, thank you for that. There's a question from Jasneet Kaur who says, do you think computational thinking, in brackets she says, which I think is more about systematic thinking, could hinder or support children to think more creatively? And then she adds, which I think is more to do with non-algorithmic thinking.
Yes.
Jasneet, could you, if you like, would you like to unmute and ask your question? Maybe rephrase it if you like, or I don't know whether you could answer the question if it's.
Yeah, sure. Well, I think certainly computational thinking is about systematic thinking, but that's not all. Very central to the definition or the working definition of computational thinking is that we should be able to, at some stage, in fact, as early as we should, formulate the problem as well as its solution in a way that the machine can take over. One of the power of computational thinking is that the machine will eventually be involved. And we should not be afraid that that happens, because the machine, when it runs on an algorithm, would not make mistakes like us. So it's important for us to be able to dedicate the responsibility of calculating all this mundane, tedious, dirty work, to the computer who always does it correctly. And then what will we do then? Sit back and relax? No. Then we really have more time to think creatively. That is what I'm saying. Learn how to make the machine work for us. That is also something that where the word computational thinking is concerned. Now, most of us would have thought that computational thinking came from Jeanette Wing. All right, it did not come from her. It actually came much earlier by this professor in MIT, and also a mathematician, a computer scientist as well, by the name of Professor Samuel Papert. Papert, in his original book of Mindstorm, actually advocated that computational thinking is actually a paradigm used to forge new ideas. That means to say that it is supposed to help you create new things. So that was the intention. So it was never about routine learning, never about algorithmic thinking. It was really always about not having an algorithm at first, but you are able to create it. So I would say thumbs up for this question, because that's exactly what computation thinking is for. And it will not hinder the child if we know how to position it. In one of the other papers that I've written, I have actually written out 4 principles for teachers to use. These are called the task design principles for invoking computational thinking in lessons. They are respectively the complexity principle, the mathematics principle, I think there's a data principle, and there's a computability principle. These 4 principles are questions that the teacher asks themselves when they start creating a lesson that is intended to factor in computational thinking in the learning of mathematics. So you can find that in the reading list as well. Thank you.
Thank you. And one last question from Anuradha, where she says that in the classes, when students sometimes solve problems, they do it without showing the steps. So I push them towards showing their understanding through the steps. More often so, that's harder for students than solving the problem itself. Do you have any suggestions for this?
I certainly have such problems as well. With my undergraduate students, also with school students as well, they hate to do that because that takes extra time. But what I would like to do is that usually I would turn the tables around. I say that, okay, now you teach your peers to solve that problem. That changed the whole scenario. When I say that, please come and teach your peers how you solve that problem, they cannot say, no, it's just this or that. They start to make an effort to make it very precise what they are doing. They will tell, oh, okay, why did I thought of this plan? How did I understood the question? They have to write it down more precisely. So giving that time for them to write down with a more purposeful intent, that is to say that they wanted to teach somebody or they wanted to present it to somebody for better understanding. I think that way helped them a lot. I mean, I certainly also push my students to write down the steps clearly. So only yesterday, one of my year 1 linear algebra kids came and say, sir, I missed out writing this step, but you deduct 1 mark. I say, yeah, this is well deserved. Why did I deduct 1 mark? Because although I know very clearly that you understood what was happening, but you did not write it down on paper. Because the moment you didn't write it down, you make me double guess what you are actually understanding. I don't want that. I want you to show me clearly that you did understand what you are doing. So it was also for the purpose of assessment that we wanted to see students' understanding be spoken aloud in words. And once they appreciate that they are doing that, then when they are giving instructions to a computer, which is what computational thinking would consist of, they have to make that instruction very precise. You can't make it very fuzzy because the computer is not there to understand what you mean by writing in this very vague form, is it? So I hope that answers your question.
Okay, so yes, thank you so much. I think we've come to the end of the list of questions. I think it has been an excellent session. I have one last question for you, Weng Kin.
Sure.
Is that in terms of how do you see this? How can we prepare? So there are these big ideas, and we need to, of course, now include computation as a part of this. But how can we scaffold and help teachers in terms of teacher preparation? Do you think there are some specific steps we should and can take to make, to enable teachers to use these big ideas in teaching?
Very good question, Jonaki. This is an excellent question. Okay, I speak it in terms of my Singapore experience, and I would like to share with you and our colleagues in India. First of all, it has to come at all angles. Step one is that because Singapore is a very small country, so when the Ministry of Education identifies that the big ideas in mathematics is important, it started first at the top level already. That actually helped things go a lot easier down in the ground level, because in the top level, they already recognize the importance of big ideas. So once that is done, a lot of the curriculum documents already write precisely what big ideas are and how these might be suggested to be translated to lessons in the school. But of course, having said that, if it is just a top-down driven kind of directive, teachers might not know what to do, because you're just giving me a curriculum with these bullet points. I don't know, I can't imagine how these bullet points transform into actual lessons in schools. And that's where you rightly point out that the next level that we need to deal with is in the teacher preparation, and as well as what we call the in-service teachers' professional development. So in the teacher preparation, that's before the student teacher go into the school to teach, they ought to already know what are these factors to consider, what are some of the educational or pedagogical framework that the teachers can pick up and to invoke, while they are aware that on the ground things may be very different, how to use those principles to create lessons for the students. But for teachers who are already out there, they may already have been teaching mathematics in a long while in a certain fixed way. And now we have a new thing like big ideas. So what they then need to do is to come back to, let's say, for example, in NIE, where there are professional development courses, where we actually talk about, these big ideas in connection with what they do in the school, how these things can be invoked. So it's a lot of collaborative effort in the fraternity of education, both in terms of the teacher preparation, that there are courses available to do that, but the teachers themselves are forming local learning communities, whereby they share with one another what they do understand by these big ideas and how these come into preparing the lessons and going through these lessons, how it affects the assessment mode, how it affects the lesson delivery, and so on. Of course, not forgetting for Singapore, parents are also a very important part of the equation. They also need to know how these big ideas are now being, carried out, in terms of the teaching in the everyday lesson. So it comes from many different angles. Yeah.
Thank you so much. Yes, I think MTA can develop some focus workshops for teachers on this theme, and I think that could be one of the next steps for us.
Yes.
So would anyone like to share any last comment before we close? It's nearly time to close to end the session. Okay, so I think we've covered all the questions. So now I'd like to take the opportunity to thank you, Weng Kin, for that wonderful presentation. It has really opened our eyes, and I think mine in particular. You've unpacked computation for us in a detailed way, and you have really made a case for why it should be a big idea in mathematics. You've talked about what it means to have a computational mindset, how we can enable it in our students. You talked about lesson consolidation, and you've also highlighted that the considered use of technological tools such as spreadsheets can actually help develop computational thinking, and also can be an interface between the big ideas in mathematics and technology and computation. And because using things like spreadsheets, help students look at ideas and concepts using multiple representations. And students can be encouraged to create a product, a mathematical product, which will actually, so it's not just giving them a tool in the hand and a ready-made solution that you use this and get answers, but you emphasize the point that we should make students develop these. And your excellent example of the quadratic calculator beautifully illustrated that. So thank you so much for this wonderful session. I know you had a very tight schedule and you fit this in between your classes. And but we do hope that in future we can invite you to India, where you can enjoy maybe in one of the future MTA conferences, where we can all discuss and meet, and we can sort of go back to the way we were, so to say, then have only this in the online mode.
Yes.
Heartfelt gratitude to you, and thanks from all of us, all the participants, and from MTA also.
You're most welcome. You have a nice day, every one of us.
Yeah, you too. Okay. And let us all join hands. Just 1 minute, Weng Kin. Let us join hands to give him. And can we, Saurabh, would it be possible for us to have a quick picture?
Yes, of course.
I'll just, can we do that? Okay, you let us know what we are supposed to do. I'll just, I think everybody can switch on their videos for a picture with Dr. Weng Kin. Just tell us when we have to be ready.
Sure. Yeah, I'll be taking these snapshots in the next 5 seconds, so please bear with me.
Okay.
Yeah, this is done. Thanks.
Thank you so much. Thank you, Weng Kin.
Right.
I do hope to see you in Prague.
Sure. Well. Yeah, me too. Yeah. Okay.
Yeah, okay.
Take care, everyone. Okay. And have a nice day.
Bye-bye.
Bye-bye.
Just one announcement for the participants. Our next session, which is a panel discussion, will begin at 12 o'clock. So we have a half an hour break. We do hope to see you back at 12 o'clock. Saurabh, are we keeping this? I think the Zoom link will be on. Or
we will keep the Zoom link on.
Yeah. Okay. So thank you everyone for a very active participation and for making the session so enriching, for asking so many good questions. And we will see you back at 12 o'clock. Thank you.
Thank you.
Thank you.